Hey, you guys, this is Professor Vid, and welcome to our lecture on Chapter 5. It's about science. In particular, there's another subtitle that the book uses often. It's called Observation or Good Observation. It's a good way to think about it. So let's go ahead and dive in. First off, why would we be studying something about science? This is a course in philosophy. This is a course in critical thinking. Why would we even be worried about science? Well, there are two reasons. The first one has to do with our principle involving garbage in and garbage out. If you don't have good observations, if you don't have good data, then you're just not going to have any good conclusions, right? So that's garbage in, garbage out. And secondly, science has been incredibly successful, arguably the most successful human endeavor ever undertaken for a variety of reasons, depending upon how you measure it. So what your criteria are, but it's certainly up there. So I've just spelled out those reasons here. First, garbage in, garbage out. We want to make sure that the observations that we make are ones that essentially keep us from fooling ourselves. And we'll learn about some of those errors in perception and memory and so forth in the coming chapters. But for now, it's still an operating principle. Secondly, we would be concerned about good observations in science because science has been, perhaps the most successful form of accessing and understanding reality that we've had to date, at least on the basis of its results, what's happened to it. Now, it's not to say that science is perfect. It's not to say that science doesn't have its biases, right? We talked about publication biases present in science in the last couple of chapters. Science doesn't answer everything. It won't tell you what the meaning of life is. It won't tell you what your favorite flavor of ice cream is. So it doesn't do everything. It's not the end all. And lastly, science is wrong. That's how it progresses, right? It gets things wrong and it moves forward. So anyone who thinks that science is perfect doesn't understand science. It's not perfect. It gets things wrong. That's what we're counting on. All that being said, it still is one of the best trains in town, right? I mean, if you don't like science, don't get on that airplane. All of the sciences are this sort of unified theory of study, and what happens in physics has to do with or can impact things that happen in chemistry, and what happens in chemistry can impact and explains things that happen in biology. So it's all connected, the natural sciences and so forth, and so we want to keep that in mind, that we might get something out of it. And if you think just on a general basis here, people live longer now, they're happier now, they have greater security now than they ever have in the history of mankind. This is unparalleled. We can travel distances within an hour that would just seem unbelievable only a couple of generations ago. And so you should just keep that in mind. It's a successful endeavor, and so maybe there's something that we can use in critical thinking in order to maximize our true beliefs and minimize our false ones. There are three components to the scientific process, the way that this book cuts them up anyway. The first is observations, the second will be tests, and then the third will be creating theories. And I'll talk about these in detail here. This is just kind of a roadmap or an overview for you guys, and I didn't want to take the space to give you a picture of a roadmap. Okay, so let's start with scientific inquiry. We'll do our first step, which is observations. It's important in science that our observations are public and they are replicable. And that's just a fancy way of saying they are capable of being replicated. So let me give you some examples. If someone says that they're psychic, and in doing so, they say, well, I can see, let's say they say they're psychic because they know what you're thinking. So you think of a number between 1 and 100, and they say, oh, it's 50, and they get it right, and then right? And you'd ask them, well, how do you know what number I'm thinking of? They might respond, well, inside of my mind, I can actually see or get a sense of, I can perceive directly what it is you are perceiving. Now, notice that we can't see what they're seeing. You never see another person's experience, but you take for granted their report of it. And so one of the problems when we look at paranormal powers, if we look at psychic powers under observational requirements provided by science, what we find is that we're not able to ever verify them, right? I cannot go inside someone's head and see for sure that they're actually reading my thoughts. I just have to believe this on the basis of what they tell me. So observations about how things behave in nature, particles and so forth, you can look at those, but if it comes down to what someone sees in their head, we just can't see inside anybody's head yet, so we're not quite sure what they're seeing. So you cannot see publicly inside another person's mind, so that would make observation of psychic powers difficult. We'd have to come up with different types of observations that might help us see such a paranormal power, because we can't see it directly. So that's one point. Secondly, take something like Bigfoot. Now, I've met people, more than one person, who told me very sincerely that they've seen Bigfoot face to face. They say they've looked at, in fact, one gentleman, he's an educator, said he looked at the creature in the eyes. He could see the creature's eyes. He looked right at it. I cannot look at his experience. All that I can do is rely upon his testimony, right? His anecdote. So if he saw Bigfoot 20 years ago, I can't go and see his impression. I have to rely upon what he says. And so it's not a public piece of information, this experience. It belongs to him only. So we have to be careful, right? In order to fit certain observations scientifically into our framework, they have to be both public and replicable. And this also goes for something like a UFO sighting, right? This is a drawing by Lonnie Zamoria. It's a very famous UFO sighting. He was a police officer in New Mexico, and I forget the exact year. It's in the 60s. I think it's the late 60s, early 70s. He makes this sighting. And he was a very credible witness. He never made any money off the sighting, and he was a police officer in very good standing in his own community. But he claimed to see this object, and it was incredibly distressing to him. And he never went back on his word. He spent his entire life saying, yeah, I did see it, and I wish I would have never told anyone about it because it caused me so much grief. Well, the problem with, say, Lonnie Zamoria seeing a UFO, no one else got to see it, right? And no one can see what he saw, in the sense that no one can share his experience directly. No one can see what he saw, so no one really knows. There's another problem, and it's with these two observations here. These observations aren't reproducible, so it's not like Lonnie Zamoria found this UFO on a dirt road, and it has never been seen since. We can't go back to that dirt road in New Mexico and say, okay, well, this is where the UFO appears. It's never appeared again, so his observation is not one that we can replicate. And so that doesn't allow it to qualify as scientific inquiry. It gives us a starting point, right? Each of these examples could give us a starting point for what might qualify or might give us a starting point for a scientific inquiry, but it's not going to count as scientific evidence because we can't see these things directly. Okay, second step in the process of scientific inquiry is going to be tests. So we make an observation, that's the first thing, and we want these observations to be public and reproducible. And then secondly, we're going to conduct tests. And these tests involve instruments to measure things, to sort of quantify them. And an important measure of these tests and instruments in these tests are reliability and validity. Now, I know what you're thinking. We studied validity last chapter. It is a completely different validity. So disregard, it's just a happy accident. But here's how these two things work. And if I ever question you on these, I'll be sure to differentiate between the two. So I'll tell you I'm talking about scientific validity versus argumentative validity, but I wouldn't worry about it. I don't think it's going to be a big issue for you guys. But there are two features of instruments that we like to have in tests. The first is reliability, and the second is validity. So let me explain them both and then give you this example over here. Reliability just means that the same instrument provides you with the same results over time. So if I have a scale, it's always going to provide me similar result for the same object over time. It doesn't weigh something and say, well, it's 5 pounds today and it's 10 pounds tomorrow. No, if it's 5 pounds today, it's 5 pounds tomorrow, and so forth, and it will keep that measurement. So that would be a reliable instrument. Secondly, we're looking at validity, and validity has to do not with one instrument giving the same result over time, but more than one instrument providing a similar result. So if I have a scale and I'm measuring an object on it, and it always tells me that object weighs 5 pounds, that looks like a reliable instrument. But I'd also need to check it against other scales to ensure that it's not just telling me 5 pounds all the time, right? If I put it down and it says 5 pounds, there may be another scale that says that object is 6 pounds. So reliability has to do with whether or not an instrument is itself consistent over time. Validity has to do with whether or not an instrument is similar in its results to other instruments. Does that make sense? Let me give you an example. Very, very famous case of Dr. McDougall measuring patients as they die in order to determine whether or not the soul has weight. So the presumption here, it's what's called a dualist view. It's that people are composed of physical body and some type of spiritual body maybe. And McDougall wants to see if he can measure this. And so what he does is he puts people on a scale. He puts them on a scale. And the moment at which they die, the scale drops. And so the idea here, McDougall thought, was that, oh, well, the soul really does have weight. It's something that we can measure. It must be located somewhere in the body. Perhaps it is a physical thing. It's a famous result, and we can use it to talk about reliability and validity. So what McDougall used for this was an industrial silk scale. And so if we want to make sure that he's conducting proper experiments, we would say, well, is the scale reliable? Meaning, does the scale give the same reading over time, right? So if I weigh myself on the scale today and it tells me I'm 157 pounds, does it tell me the same thing tomorrow when I still weigh 157 pounds, right? Now maybe a better example would be a ball or something like that might not vary too much in weight, but you get the general idea. Does the scale give the same result for the same objects over time? Then if we want to know about these scales that he's using, we would ask whether or not these scales are valid. In other words, do these scales give the same sorts of readouts that or measurements that other scales would give, right? Maybe there's another industrial silk scale that's far more accurate, and that would determine whether or not our test was proper, our measurements were proper. Now, why does this matter? Well, when you're conducting a test and you're measuring something, you need to make sure that you're properly measuring it, and this helps to avoid some of the pitfalls that we'll come up with later. It's a little bit difficult to explain that part, but there are reasons why we want our instruments to be accurate in this way. And so there are protocols in science for the way instruments work so that it avoids or gets around us making some simple errors. Okay, a couple of other things about tests here. It's important that tests ask the right question. And there is something called the falsifiability criterion, which we will continue to talk about a little bit, but it's fairly important. In science, you have to be able to test something. It can't be something that is incapable of being checked out. So let me think about this. Let's talk about, hold on, I've got a little bit of fighting here going on in the background. Okay, so let's talk about scientific inquiry with regard to tests real quickly. The first point is you want to ask the right question in science, and usually that means you want to ask a question that you can find out the answer to. So if for example, I told you that there was an invisible dragon in my house, and I wanted to test this scientifically, you'd say, okay, well, if it's an invisible dragon, it's invisible, but maybe it weighs something. So we could install a bunch of sensors in the ground in my home, and that would allow us to measure the weight of this dragon. well, then I tell you, well, the dragon has no weight either. You can't weigh it at all. It's invisible and it doesn't have any weight. Then you might say, well, okay, well, we'll still test it another way. We'll fill the room with a colored gas, and then everywhere that is not the dragon, we'll see an outline of the dragon or something like that. And then I say, well, actually, it's more complex than that. The dragon doesn't have a physical form of any kind. Well, now it's impossible to test for this dragon, right? There's no way to find out whether or not it's true. And this happens a lot when people are concerned with, for example, unidentified flying objects. If I saw a UFO in the sky and it appeared, and I tell you I saw it 10 years ago, there's really no way to test for that, right? I mean, how could you possibly test? It happened 10 years ago. There's nothing that you can do to verify it. You would just be taking someone's word for it, and that's related to a problem with testimony and anecdotal evidence. But okay, so that's just an important point. Falsifiable results are ones that we want in science. We want to be able to test something against reality. You want to be aware of ad hoc hypotheses. The book does a good job of talking about that. And also, the burden of proof is with the claimant. So if I make a claim that apple juice cures cancer, I need to prove that. I'm the one who needs to prove that, not someone else. So if I'm making the claim that there are psychic powers, then I'm the one who needs to support that with evidence, right? Okay. Secondly, in science, it's important to rule out alternative explanations. And for us, we can think about that as alternative causes or other reasons for something. So we will often have, in fact, all the time, there are scientific studies that are conducted on prescription medicines. And in order to determine whether or not those medicines are effective, scientists will have a control group. In other words, a group of people who do not receive the medicine. They receive sugar or placebo of some kind that doesn't have the active factor. And that way, we can test whether or not the medication does anything, because we can see people who get the medicine and see what happens versus the people who get none. And sometimes, in fact, sometimes often, there is no difference between the group that gets the medicine and the one that doesn't. Well, that should tell you then it should tell you something about the medication, that probably or perhaps it doesn't work, assuming the rest of the test is validly constructed. There are double-blind procedures in place whenever we conduct a scientific test. So continuing this analogy concerning medication, the doctor administering the medication doesn't know whether or not that patient is getting the active medicine or a placebo. And that's because it would color or change how the doctor perhaps sees the patient or how they interpret results from that patient. And so they do double-blind procedures where the person who is receiving the medication doesn't know whether it's the real medication or the placebo, and the person administering the medication doesn't know it either. And then it's important that we look out for stimulus leakage. Now, I'm not going to spend a lot of time on this, but essentially he's talking here about psychic experiments. So we're talking about Zener cards. If you remember Zener cards, it's just a shape on one side of a card. And sometimes, certainly there was a series of very famous tests conducted at Duke University, and they purported to show that certain individuals were psychic. But when they looked closely at the cards that they were using, they saw that if you held them up to the light, you could actually see through them. Well, then an explanation for someone doing very well on that test is not that they're psychic, it's that they can see through the card when it's being held up. Okay, and then an important component of a test is to test the right people or to test the right subjects. If you are testing a medication for diabetes, it's incredibly important that you get the proper patients, right? So you need patients who have the appropriate form of diabetes, right? Is it type 1 or type 2? If the medication is a type 1 medication, then it shouldn't be given to people who are type 2 diabetics, right? So you need to test the right people, and you need to do so in a random way. Okay, let's talk about scientific theories. Okay, you guys, so let's talk about some important features of scientific theories. The first one is falsifiability, testability. Remember the dragon example where I said there was this thing, this dragon, but there was no way to test for it. There was no way to know whether it was there or not. How would that be any different than there not being something there at all? And occasionally this will happen. People will talk about energy forces and so forth. But when you ask them what they mean specifically about the energy, is it electromagnetic? Is it strong force? Is it weak force? Is it gravity? They say, no, it's something else. And you say, well, how do you know that it's there? How can you detect it? And somebody says, well, you can't detect it yet. Well, how would that be any different than there being no force at all? I mean, if you can't detect something, whether it's a dragon or a force, how is that different than there not being anything there at all? You wouldn't know if it's there, even if it was. So that kind of, if something is not testable, it sort of heavily undercuts it. Next, we have productivity, whether or not a test is productive. And what this really means is, does the test tell us something that is unexpected? Does it tell us something that should happen if the theory is true? And then, son of a gun, the theory is true. A great example of this is Einstein's theory of relativity. And what it tells us is that clocks that are moving faster are going to work at a different rate than clocks that are standing slow. And it turns out this is true. Clocks and satellites have to be set a little bit differently because they're traveling so much more quickly around the Earth. Okay, comprehensiveness of a theory is important. How much of a theory, how much is being explained by a certain theory. So, for instance, the theory involving, we'll just say the heliocentric theory of the galaxy, right, is a very good one because it explains a lot about how not just Earth moves, but other planets move, right? And it explains a lot about tides and so forth. Well, it does in a sense, right, in a way. It won't qualify that completely, but the two are related. I won't say that unequivocally, but they are related. But the point is, the more a theory explains, the better it is. And then, lastly, we sort of have this, we always prefer simple answers. And this is, in a way, just an application of Occam's razor. But it is an important point, and it's kind of the point of the course. Sometimes we have a scientific theory that's really, really good, except for a couple of cases, residual cases, results that we can't quite explain with the theory. Those are called anomalies. They're anomalous. They're unusual. Those results are what we want to focus on because that's where our theory is falling apart. And so what happens is, usually in the history of science, these anomalies or these strange cases kind of pile up over time until we have to change our theory because our theory then becomes incapable of explaining these results, and that theory gets replaced by another one which is able to explain those anomalous results. Okay, last bit here on science. So our author refers to this as Sagan's balance. I'll be honest with you, I've never heard it referred to that way. I think he just needed a name, but it's just the claim that that's just the rule that extraordinary claims require extraordinary evidence, and we covered that in some detail earlier, so I won't beat you to death on that. And then he also talks an awful lot about the Fed's standard, and the Fed's standard is basically a standard that applies to research that involves paranormal claims, and it's kind of similar to Occam's razor. But the idea is if someone's making a paranormal claim and it's going to be subjected to scientific scrutiny, you need to have expert, independent, and impartial supervision of that exam so that you can eliminate fraud, you can eliminate error, you can eliminate deception, and you can just eliminate sloppiness. And as you'll find, usually, if someone's, well, yeah, I'll just leave it at that. And got to know when to say when. Okay, so this covers the end of chapter 5. It's a somewhat shorter lecture, and I hope it's sufficient for your purposes. When you watch this lecture and you read it in conjunction with the chapter and you study them both, you should have sufficient material in your mind to take the exam. Okay, thanks very much, you guys, and I look forward to any questions you have. If you have them, go ahead and email me, rvitt@lbcc.edu.